continuation of your notes for 5.1, extreme values of functions. So now we're doing example 3, find the absolute maximum and minimum values of the function below on the interval -2 to 3. So we need to list out the critical points. I know this wasn't included as far as critical points go, but anytime you are finding absolute maximums and minimums, you need to consider your endpoints if you are on a closed interval. So I do need to consider f of -2 and f of 3 whenever I'm finding my absolute min and my absolute max values. This interval is closed, and this function x to the 2/3 power is continuous on this interval, so it is definitely going to have an absolute max and an absolute min. To find the other possible candidates for our absolute max and absolute min, we need to take the derivative. So the derivative here is going to be 2/3 x to the -1/3 power. We would set this equal to 0, and I'm actually going to rewrite this because this is 2 over 3 times the cube root of x. So this solution, or this problem, has no solution. Because whenever you're setting a fraction equal to 0, to make that fraction 0, the top you would set equal. Well, 2 equals 0, that has no solution. So this function is actually never going to have a derivative that's equal to 0. However, remember, the critical points also include places where it's not differentiable. Got too many squirrels there. This is not differentiable where the denominator is equal to 0. So it's not differentiable at x equals 0. X equals 0 is in the interval that was provided to me in the original setup of the question. So that also has to be one of the candidates that we consider here. So now to actually find our absolute min and absolute max values, we need to plug these in. So f of -2 is going to be -2 to the 2/3 power, which is the same thing as 4 to the 1/3 power. So the cube root of 4, basically. This one, 3 to the 2/3 power, is 9 to the 1/3 power. Well, 9 to the 1/3 power is greater than 4 to the 1/3 power, so this would be my leading candidate right now for maximum. And then when I plug in 0, I get 0. 0 to the 2/3 power is just 0. So based on these findings, and again, using the knowledge that I have to have an absolute min and an absolute max, I have an absolute max of 9 to the 1/3 power at x equals 3. Notice I did state what the absolute max was and then where it was. Make sure you always state the location. And then we have an absolute max of 0 at x equals 0. And those would be your solutions there for that question. There will be times, especially if they don't give you what the original problem is, you may only be able to state where the absolute min or absolute max would occur, maybe not necessarily what the absolute min or max is, so just make sure you are reading the question and answering it how it wants you to answer. This one says find the extreme values. Notice it doesn't say absolute extreme values, so we could be looking at locals as well as globals of this function. It doesn't give me a domain, but this function does have a domain. This is only going to be defined when this 4 minus x squared is greater than 0. This does not exist at 0 because it's in the denominator. We can't have 1 over 0, so that's why there's no line under this inequality. So even though it's not stated, my domain here is -2 to 2. So just something to keep in mind whenever we're going through. I am going to rewrite this to make it a little bit easier to take the derivative. So this is 4 minus x squared to the negative 1/2 power. Because my endpoints are not included, I'm not going to be including those in my possible candidates for the absolute extreme values because I can't plug them in. If I plug them in, I get something that's undefined. So I'm only concerned with where my derivative doesn't exist. By the way, when you're looking where the derivative doesn't exist, you're only looking at places that are in the original domain that are then excluded when you take the derivative. And then we're also going to be looking at where the derivative is equal to 0. So this is going to be negative 1/2, 4 minus x squared to the negative 3/2 power, because again I have to subtract 1 from the exponent. And then I'm going to multiply by, using the chain rule, the derivative of the inside, which is going to be negative 2x. So if I rearrange this, the negative 1/2 and the negative 2 are going to multiply to 1. The x is going to stay on the top, and then this quantity is going to move to the bottom. So the derivative would not exist where this is negative or equal to 0, but that's going to be the same domain that I had from the beginning, so there's nothing additional that I would use to plug in. However, at 0, I am going to have something going on, possibly, because that is the value that would make the derivative, or it has a, trying to think of a way to word this. The derivative is equal to 0 at x equals 0. So that is actually going to be the only candidate that I look at. So whenever I plug that in, I get 1 over the square root of 4 minus 0 squared, which is 1 over the square root of 4, which is 1/2. So now you need to figure out, is this a min? Is it a max? Is it absolute? You could look at the graph, possibly, if this was a question that allowed graphing calculators. But if I look at, say, 1 or negative 1, I would have 1 over the square root of 3, and then negative 1 over the square root of 3. Both of those are going to be higher in value than 1/2. The square root of 3 is like 1.7. So 1 over 1.7 is going to be a greater value than 1/2 is. If you actually look at this graph, it's going to look something like this, I believe. So this is actually going to be an absolute max. I'm sorry, an absolute min. I even just said min. It's also a local. So it's still going to be a local min, but there is no maximum on this because of the fact that your endpoints here are not included. There is no local or absolute maximum values for this function. We'll be doing more with number lines to prove whether things are mins or maxes. So if you're not quite sure about that yet, no worry about that. Okay. So this is another important statement. A function's extrema can only occur at critical points and endpoints, but not every critical or endpoint is going to signal the presence of some extreme value. That's why it's important to test them and make sure that there is something actually going on there. And that's covered on page 197. So there's a couple of different ways you can do this. Usually we use number lines and check something just to the right and just to the left to figure out if it is actually the highest value in a region or the lowest value, depending on if you're checking for maxes or mins. Okay, this brings us to example 5. And I saved a little bit of time by graphing this. We want to find the extreme values of the function that's given here. So we have the first piece is the 5 minus 2x squared if x is less than or equal to 1. And then the x plus 2 if x is greater than 1. So at 1, they do have the same value. That is a corner there. So one of the candidates that I would have for my possible extreme values is going to be at 1 because it's not differentiable there. So if we take a look at the derivative, and I believe the book actually goes through and works out the definition of derivative, but I don't think that's necessary now that we know the shortcuts. So the derivative of this top piece is going to be negative 4x, and that's going to be the derivative if x is less than 1. I can't include 1 because it's not differentiable at 1. The second piece has a derivative of 1, and that's for all the x's that are greater than 1. So if we look at the top piece, so 0 is one of the places where f prime is equal to 0. If I look at the second piece, the derivative of the second piece is just 1. So this one is never going to be 0. There's no place where the derivative of the x plus 2 is going to equal 0, so we don't get any critical points from that. So our only critical points that we have are at 0 and at 1. Well, you can see at 0, I'm going to return a value of 5. At 1, I'm going to return a value of 1. Because of the way this graph is set up, because you have an arrow going continuously down and an arrow going continuously up, these are both local extrema. So we actually have a local max of 5 at x equals 0, and a local min of 1. I'm sorry, that's not 1, that's 3. Wasn't even paying attention to my own work there. At x equals 1. Because there are places where the values are lower and the values are higher, these are locals instead of absolutes. So you want to make sure that you are careful when you distinguish between those. I feel like I've been saying you got to be careful a whole lot, but I can't stress it enough. You really have to be careful with your math when you're going through here. Now we have example 6. Find the extreme values of the function given below. So we have f of x is equal to the natural log of the absolute value of x over 1 plus x squared. The only domain value that is excluded is 0, because that would make your fraction 0, and you can't take the natural log of 0. We don't have to worry about negative numbers here because you have an absolute value. This is going to be a little bit more complex as far as a derivative goes than what you might be used to dealing with. So that's just something to keep in mind here. So for my derivative, remember this is 1 over what you're taking the natural log of times the derivative of the inside of that natural log. Well, that's a quotient rule, so we have to go through and do low d high minus high d low all over low squared. So that's going to be the entire derivative of the inside, and then we have to go through and simplify this. So for this first part, this fraction is actually going to flip. We have 1 plus x squared over x, because that's 1 divided by that is equal to. And then I have to simplify over here. I forgot my square there. 1 plus x squared squared. This is going to be a minus 2x. So we have 1 plus x squared minus 2x squared. So this is going to be 1 minus x squared on top. When we go through and simplify, we have this 2 and this divide out. So I'm left with 1 minus x squared over x times 1 plus x squared. Then we can finally set our derivative equal to 0. So the only places where the derivative would not exist would be 0, which wasn't in our original domain, so I don't have to worry about that. So now I'm really focusing on what would make the top 0, which is plus and negative 1. Those are going to be the places for my extreme values. So if I take those and plug them in, f of 1 and f of negative 1, well, if I have f of 1, that's going to be the natural log of 1 over 1 plus 1 squared. So that's going to be the absolute value of 1/2, which is just natural log of 1/2. Or a negative natural log 2, if you wanted to think about it that way. If I do negative 1, again, I have an absolute value. So that's negative 1 over 2, again, which is still natural log of 1/2. So both of these give us the same value. Again, we can't plug in 0. But if I plug in anything bigger, like a 2 or a 3, 4, you're going to end up with something that is less in value than the natural log of 1/2, because you'd be taking the natural log of a fraction where the decimal value would be less than 0.5. And if we go in between, so like 0.5 itself, that is also going to be a lesser value. So these are actually maxes. So we have, and if you look at the graph here, let me scroll down here a little bit. So I actually have the graph down here. This is what your graph is going to look like. So because of this, and again, this is where your derivative is undefined because it's an infinite discontinuity there. You have two places where you have absolute maxes because they're the same value. You have absolute max of natural log of 1/2 at x equals plus or minus 1. Instead of natural log of 1/2, you may see that as negative natural log 2, because this is the same thing as natural log 1 minus natural log 2. The natural log of 1 is 0. So that's why it's negative natural log 2. You can see that there. This one is a little bit more involved, and again, we could do a number line to confirm that those were absolutes as well. So lastly, here's your homework. This assignment is going to be due on Monday, December 14th. Answers will be in Schoology, just like with all the other work that we've done. Go back through, read the notes, watch the first video, watch the second video. There should be some other examples out there online. This whole section that we're in chapter 5, we're going to be doing a lot with applications. The first 3 sections kind of all go together. 5.1, 5.2, and 5.3 all deal with extreme values, mins and maxes. We're going to be looking at inflection points, which are called turning points, and putting it all together. Then once we get into 5.4, then we're actually going to start looking at some different types of applications rather than just the straight theoretical stuff, which is what the first half of the chapter mainly covers. So go back through, rewatch these if needed, reach out to me if you have any questions at all.